They store charge. Capacitors have capacitance, which means they have the capacity to store charge. Now, maybe if we say that a little more simply, we can say that something that has the ability to store charge and an object that has the ability to store charge has capacitance. So we often like to say capacitance is the ability of an object to store electric charge. And we have in electronics these special devices that can store charge that can later be used to run an electronic device. Okay, now the symbol for capacitance is a C. The metric unit is a farad. We abbreviate farad with an F. So the capacitance is C. Now that might seem pretty straightforward, and it is, but remember the symbol for current, which also starts with a C, is an I, and the symbol for charge, which also starts with a C, is Q. But C and C, capacitance, farad, F. Now, farads are a measure of the number of coulombs of charge, another C word, coulombs of charge that can be stored for every volt. So you can store a certain amount of charge on a capacitor based on the capacitance of the capacitor and how much voltage it's hooked up to. 1 farad, kind of as a base, 1 farad means if you have a 1 farad capacitor, that means you can store 1 coulomb of charge for every volt that it's hooked up to. So a farad is actually an abbreviation for coulombs per volt. Just like volts is joules per coulomb, farads is an abbreviation in itself for coulombs per volt. And this is the equation we often use it in, the capacitor equation. Q, which is charge, is equal to the capacitance. This C is the capacitance time.
This one I am just telling you that Q equals to C into V, where the Q is charge, C is just capacitance, and your V is applied voltage. So according to that equation, you can easily find out the capacitance of capacitor is C equals to Q by V, where Q is measured in coulomb and V is voltage. So capacitance is what? It's a coulomb per voltage. Now the next question, answer 5, which is the example. First of all, just take the data whatever the given to you. Wherever line voltage is the 300 voltage. See, whatever the basic voltage given to you becomes your line voltage, or this one is your inducting voltage. Then the applied external voltage is the 230 voltage. So using these two value, we can just solve our question. At the resonance circuit, there are two types of resonance circuit, series and the parallel. So first of all, here we have to just prove for the series resonance circuit, where the VL equals to VC. The voltage for the inductor is same as the voltage for the capacitor because it is a series circuit. So your VR and your VR becomes your V. Resonance voltage is your V. So according to that these values, we can just find out our next given parameter. So the voltage we have to just find out the voltage across the capacitor. The voltage across the capacitors are the VL equals to we have just the value that VL equals to VC, and we have the value of VL equals to 300 volts. So that become the value of your capacitor. So ultimately you will just find that VC equals to 300 voltage. Now again the voltage across the resistor. Here there is a mistake, that not a capacitor, there is a resistor, and we have the value of the applied voltage V equals to 230. So that one become our resonance voltage, that is VR. So ultimately we just get the value of VR equals to 230 voltage. Now the next question, that is a Q factor. The Q factor is known as the quality factor. It is a index of the quality, which defines directly the material quality of your material. So Q factor is the quality factor, or the storage factor is also known as the figure of merit. The figure of merit is a which gives the how your material, how your device is effective or it is useful. It is the ratio of the inductive reactance to the resistance of a coil. So by taking the ratio of the inductive reactance XL to your resistance of a coil, there is the inductor, then you can just find out the Q factor. This is the equation of the Q factor, XL inductive reactance and your R resistance for the coil. You can also write like that, the WL by R. There is no unit for the Q factor, so it's a unitless. It is only the number which indicates the quality of the coil. Q factor is always given with the number. So according to that number, you can just tell about the circuit or the device, how the device is useful or how the device is corrective. If the Q factor of the coil is higher, it means the reactance of the coil is very less, because your Q factor is directly proportional to XL inductive reactance, but it inversely proportional to the resistance of the coil. So if the Q factor is increased, your R is decreased. It means the resistance of the coil is less. So it ultimately says that if you want to improve your Q factor or the index or the quality of the index, then you have to make your coil of the resistance is very less. Hence, you can also say that it consumes the less power, because P equals to I square R. So if you are making the size of the resistor is very less, then it consumes the less power, and if your power loss is less, then the heat generated to that material is very less. So it means that the accuracy goes higher and the reliability is also improved, and so the reliability and the accuracy goes higher, then definitely the Q factor, the quality of that material is increased. So ultimately, if you have, so the concluding section is that if you want to improve the quality of your material or the device, you should keep your resistance of the coil is less. The next question, the relation between the line voltage and the line current, phase voltage and the phase current in a polyphase circuit, or the star and connection in a three-phase circuit. But before going to that example or the question, just some of the important terms related to that topic, just we go through that topics. The first of all, the idea about the phase voltage. The polyphase circuit has the generally 3 phase, 6 phase, but here we are talking about the 3-phase circuit. Generally the 3 phase are known as A, B, C, or you can say that the R phase, Y phase and the B phase. So what is the phase voltage? The voltage is across the 2 terminals of any one winding is known as a phase voltage. So you are just taking any 2 winding of a phase, 1 phase of the 2 winding, then the voltage generated that 2 phase is known as a phase voltage. The line voltage, the potential difference between any 2 lines is known as a line voltage. The line current, the current flowing through any one line is known as the line current. The phase current, the current flowing through any one winding is known as the line current, phase current. Friends, here the line current, line voltage, phase current, phase voltage, all the values of that terms are related to the what kind of connection you are preferred. Either you are preferring the star connection or the delta connection. I am just showing you with one figure. This one is a neutral point. These are 3 phases like R phase, Y phase and B phase. This is neutral. R, Y and B. So these are the 3 phases and these are the 3 lines. So the voltage between R and Y line, VRY, is known as the line voltage between the R and Y. VYB, between the line Y and B, and VRB, line voltage between the R and B. So these are the line voltage, and whatever the current flowing from that lines IR, IY and IB, this is known as a line current. Whatever the current flowing from that phase is known as a phase current, IR, IY and IB. So this is the phase current, and the voltage between the any winding and the two phase, say RN neutral. So VRN, this is the phase voltage between the B and N. This is known as VBN, the phase voltage, and this one is V, voltage between Y and neutral, that is N. So these are the star connection. You can also draw same way as for the delta connection. So here you are just getting the idea about the line voltage, line current, phase voltage and the phase current. Now the relationship between this line voltage and line current, phase voltage and phase current for the, first of all, for the star connection. The line voltage is √3 times greater than your phase voltage for the star connection. So line voltage is indicated with the VL and phase voltage is indicated with the VPH. So the equation such like that, VL equals to √3 times VPH, or you can prove that VPH equals to VL by √3. Friends, the voltage in a star connection is same for the current in a delta connection, and whatever the voltage in a delta connection, that becomes the current in a star connection. So this is the relationship, somehow the reciprocal with each other. Now the current in a star connection, see here the line current is same as the phase current in a star connection, as we already shown in a figure for the star connection. So your IL, that is the line current, becomes your IPH, this is a phase current, or you can also write like that, the IPH equals to IL. Now I am also telling you that that relationship or that equation is same for in a delta connection, but for the voltage. The delta connection, see here the line voltage is equals to the phase voltage. What exactly, as we seen previously, that the line current equals to phase current. So that one is same as in a delta connection, but for the voltage parameter. So we can write like that, VL equals to VPH. But if we are talking about the voltage for star connection, that one is the VL equals to √3 times VPH in a star connection. But for the delta connection, they are the same. Whatever your phase voltage, they become your line voltage, and whatever your line voltage, that become your phase voltage. But that is not happen for the current in a delta connection. Your line current or your phase relationship between the line current and the phase current are such like that, your line current is √3 times greater than your phase current, or you can write like that, your phase current is √3 times lesser than your line current. So the equation such like that, IL equals to √3 times IPH, or IPH equals to IL by √3. So these are the relationships of the line current, line voltage, phase current and phase voltage for the star connection and for the delta connection. Friends, keep in your mind, this relationship is differ for the different kinds of connection. What the connection you are preferring, either you can prefer the star connection or you can prefer the delta connection. Video for the star connection or the delta connection.
Data network and star network. If the resistance is connected in this way, it is delta network, and the resistances which are connected this way are the star network. To solve electrical network, or to find out the equivalent voltage or current through the network, we need to solve the complex networks. At that time, we need to transfer a delta network into star network or vice versa. So delta network can be converted into star network by using these three formula. The resistances in delta network can be converted into the star network resistances by using these calculations. Here R1 will be equal to R12 into R31 upon the summation of all the resistances. R2 will be equal to R23 into R12 divided by summation of all the resistances. R3 will be R31 dot R23 upon the summation of all the resistances. Now we will see how a star network is converted into delta network. The resistances in star connection can be converted into the resistances in delta connection using these three formula. So to make a simple circuit from a complex circuit, we use these formula.
The next question, the question number 2a, prove that for the pure resistive circuit, this is for the only single phase, not for the three phase, the power consumed for that circuit is P equals to I square R. This is the common equation for the power dissipated from the circuit, but we have to just prove for the pure resistive circuit why it is P equals to I square R. Starting with the solution, first of all, there is a value like an instantaneous voltage of the power. Now what is the meaning of instantaneous value? Instantaneous, it means that the value are changing with the different instant, or these are the value of the continuously changing. Just I am telling you. For the voltage, starting with the reference line 0, you can see that the value of the voltage is starting from the 0 and gradually it increase. Suppose there is one